Hi friends, this is Rizan Kagri and welcome to our lecture series of Basic Mechanical Engineering. In our last session, we have discussed about thermodynamic laws, that is first law and second law in detail. Okay, now in today's session, we are going to study calorific values, that is types of calorific values, and then after numericals based on our topics which we have discussed. So now first question on the spot comes in our mind, that what is calorific value? So this is specifically for 1 kg of a fuel. Remember, 1 kg of fuel, any type of a fuel. It could be a coal, petrol, diesel. Okay, so let's see its definition. Calorific value is defined as a heat energy evolved or released by complete combustion of a unit mass of a fuel. So unit mass means for 1 kg fuel. So taking a simple case, that 1 kg of coal, when it is completely burned, then whatever heat energy is released by burning that coal, that heat energy is called a calorific value. Okay, but in actual practice, we would say that certain portion of fuel is always going to remain unburnt. Okay, well, as we know that coal is a low grade fuel. Okay, that is types of coal we know: anthracite coal, bituminous coal, lignite coal. So every coal cannot be burned completely. Okay, there will always be certain unburnt portion. So the actual heat energy released by burning of fuel will always be less than the calorific value. And with respect to that, there is an efficiency called a thermal efficiency. So thermal efficiency is the output upon input. Okay, that is output means whatever heat energy that has been released by burning of fuel upon input means a maximum heat energy that can be obtained by complete combustion of a fuel. Okay, now types of calorific value. So let's see. The first type is high calorific value, and the second name is low calorific value. Now to understand that what is high calorific value and low calorific value of a fuel, we need to think about its composition, right? The composition of fuel. So we know that fuel has a hydrogen and carbon link present, that is a hydrocarbon link, and it can be burnt, or a combustion can only be done in presence of oxygen, that is when air is present in surrounding. Now whenever a combustion takes place, so we know that hot gases will be generated which will be possessing a heat energy. But whenever a combustion takes place, then at that time the hydrogen which is present in fuel and the oxygen from a surrounding also reacts to form a byproduct, that is H2O. Yes, that is water vapor, which means that water vapor is also generated along with generation of heat energy. So this water vapor produced along with the product of combustion when condensed means cool down. So what is going to happen when a water vapor is cooled down or condensed? So we would say it is going to be converted into a liquid form, right? And when it is converted into liquid, then at that time heat energy will be released from water vapor. So that heat energy released along with the heat energy produced because of complete combustion, that summation of both the heat energy, that is the heat energy released by condensation of water vapor plus the heat energy released by combustion of fuel, is contributing to a high calorific value. So as you can see on your screen, the definition of high calorific value I have written, that is heat energy evolved by complete combustion of a unit mass of a fuel and the product of combustion along with water vapor are condensed or cooled down up to normal condition, that is STP condition, standard temperature and pressure condition. Then what is going to be released? Then heat energy will be released, that is a latent heat as well as a sensible heat will be released. So this total heat energy that is produced due to combustion as well as due to cooling down of water vapor contributes to a high calorific value. Whereas in a case of low calorific value, if the water vapor released are not cooled down, and are directly rejected to the surrounding atmosphere without cooling or without condensing it, then a heat energy generated will only be due to the complete combustion of fuel. So that heat energy generated is called a low calorific value of a fuel. So as you can see, definition: heat energy evolved by complete combustion of a unit mass of a fuel and a product of combustion are released to the surrounding atmosphere without condensing the water vapor. So we get a heat energy only due to complete combustion of a fuel. That is called low calorific value. So up to this we have seen our theoretical portion of our chapter 1. Now let's start with our numericals of this chapter. So the next topic, let's see question number 1. Now as you can see on your screen, the question is shown: an artificial satellite of 600 kg is moving towards moon. We need to calculate its kinetic energy and potential energy with respect to Earth when it is at 50 kilometers from a launching position and it is moving at a speed of 2500 km per hour. It has been given in the data that we need to take gravitational acceleration, that is small g is equal to 7.9 meter per second square. So first of all you have to write the data. So data given is mass of a artificial satellite, that is 600 kg. H is given, that is the height of a satellite from its launching position is 50 kilometer. Okay, and velocity is also given, that is 2500 kilometer per hour. We need to find out a kinetic energy. So it is a direct application of a formula. We know the formula of kinetic energy, that is Ke is equal to half mv square, and that of potential energy is mgh. So mass is already given, velocity is also given for kinetic energy. Similarly for potential energy, mass is given, g is also given, and height of an artificial satellite from its launching position is given, that is 50 kilometers. So you have to remember that we are going to work in a SI system, that is international standard. So I have converted height into meter, that is 50 to 10 raised to 3 meter, velocity in meter per second. So it is given kilometer per hour. So converting it into meter per second, we get 694.44 meter per second. So substituting the value for kinetic energy, we get half mv square, where mass is 600 kg, substituting velocity 694.44 the whole square, we get answer 144.67 into 10 raised to 6 joule. So 10 raised to 6 joule is mega. So I have represented by 144.67 megajoule. This is our final answer of kinetic energy. And similarly potential energy, it equals to mgh, which is equal to 600 into 7.9 into 50 into 10 raised to 3. So the final answer is 237 megajoule is the potential energy of that artificial satellite at a height of around 50 kilometers from a launching position. Okay, so this question has been asked in your GTU examination, final exam. So you have to do this. Now let's see our next numerical. Question number 2. So it is on your screen. Now the question is given that in a compression process 3 kilojoule of mechanical work is supplied to 5 kg of a gas. Okay, the heat rejected to the surrounding is 700 joule. You need to calculate change in specific internal energy. The data given is work input. Now work is supplied, which means work is done on the system. So as we know that whenever work is done on the system, it is considered negative, and work done by the system is considered positive. Similarly, heat is rejected to the surrounding by the gas, which means heat energy or gas has lost its energy. So it is considered negative. So I have written Q is equal to minus 700 joule. And mass is given, that is 5 kg. Now we need to find out a specific delta U. So when a specific term is used, the first question is that. So a specific term is used for 1 kg of a fuel or a 1 kg of any fluid. Okay, so first of all we will find out internal energy for a 5 kg, and then after for 1 kg we are going to divide that answer by 5. So this is very simple application of our first law, that is Q is equal to delta U plus W. Applying that law, minus 700 is equal to delta U minus 3000. So answer of delta U is equal to 2300 joule. Okay. So this change in internal energy is for 5 kg, but for 1 kg it will be how much? So specific delta U is equal to 2300 divided by 5. So we get an answer 460 joule. So this is the final answer. Okay, so I hope that this numerical is clear. This is just an introduction that you need to keep in mind the sign convention for a work transfer and for heat transfer. Now let's see our next numerical, that is question number 3. So as you can see on your screen, question number 3, a gas enters the system at an initial pressure of 0.5 megapascal and a flow rate of 0.15 meter cube per second, and it leaves at a pressure of 0.95 megapascal and a flow rate of 0.09 meter cube per second. So flow rate is basically a discharge, that is a volume of a fluid passing in 1 second. Okay, during this there is an increase, or during this process there is an increase in internal energy by 22, that is of 22 kilojoule per second. You need to calculate change in enthalpy of a gas. So calculate change in enthalpy means the direct answer comes delta H is equal to final state enthalpy minus initial state enthalpy, that is H2 minus H1. Now over here, the first thing which we need to keep in mind is a conversion. Joule means Newton meter, remember, okay, whereas pascals means Newton per meter square. So whenever there is joule, then you need to take pressure in Newton per meter square or pascal, and whenever there is kilojoule, then you need to take pressure in kilonewton per meter square or in kilopascal. So as you can see that the internal energy given is 22 kilojoule per second. So with respect to that, we need to take pressure in kilopascal. Okay, so I have converted megapascal into kilopascal. So you can see the data. P1 is equal to, I have written 0.5 into 10 raised to 3 kilopascal. P2 I have written 0.95 into 10 raised to 3 kilopascal. V1 I have written, that is volume which is given, flow rate at an inlet initial is given 0.15 meter cube per second. V2, that is at an exit, the flow rate or a volume that is flowing is given, that is 0.09 meter cube per second. Delta U is given, that is 22 kilojoule per second. We need to find out delta H. So we know the formula of delta H, that is final enthalpy H2 minus H1. Now what is the formula for enthalpy? So as we have discussed, enthalpy is equal to summation of internal energy and flow energy. So I have written at an exit final state enthalpy will be U2 plus P2V2 minus U1 plus P1 V1. Arranging the terms, as you can see on your screen, I have written U2 minus U1 plus P2V2 minus P1 V1. Now while solving this, first of all we can find out P1 V1 and P2 V2 separately. So I have find out separately, that is P1 V1 is equal to 0.5 into 10 raised to 3 into 0.15. So the answer of P1 V1 will be 75 kilojoule per second. Remember, volume is meter cube per second, so the answer of P1 V1 will also be in kilojoule per second. Similarly, we get P2 V2 is equal to 85.5 kilojoule per second. Now we have found out P1 V1 and we have found out P2 V2. Now we can directly substitute in our equation of delta H. So as we know, U2 minus U1 is what? That is change in internal energy which is given, that is 22 kilojoule per second. So substituting a value, we get 22 plus 85.5 minus 75. So the final answer of delta H is 32.5 kilojoule per second. Okay, so I hope that you are clear with this solution of question number 3. Now let's see our next question, that is question number 4. Now look at your screen. The question is given, a manometer is used to measure pressure of a gas in a cylinder. The manometric liquid has a specific gravity of 0.9. The height of a column is 350 mm. Determine absolute pressure of a gas. You need to take atmospheric pressure is equal to 101 kilopascal. So over here, the data given is a specific gravity. Now this term you have studied in your 11th standard fluid mechanics topic. We know specific gravity S is equal to density of a fluid upon density of some standard fluid. So whenever the fluid used is a liquid, then with respect to that, the standard fluid we are going to take water. Okay, and whenever a fluid used is a gas for pressure measurement, then a standard fluid will be taken as air. Okay, now as we know that a manometer is a device which is used to measure a gauge pressure. Okay, so gauge pressure, as you can see on your screen, I have shown a diagram which I have already discussed. Point A represents a point where we can find out a gauge pressure. Okay, so with respect to that, what is an absolute pressure? So it is equal to atmospheric pressure plus gauge pressure. Okay, that is our absolute pressure. Now to find out absolute pressure, our first target is to find out a gauge pressure, because atmospheric pressure is already given in a data 101 kilopascal. So how we can find out gauge pressure? So for determining gauge pressure, we know the formula of pressure, that is rho GH. That is, rho is a density of a fluid used. So it is given that manometric liquid has a specific gravity 0.9. Now by using specific gravity, we can find out the density of that fluid. So as you can see on your screen, I have found out that is 0.9 is equal to density of a fluid upon standard fluid, that is our water. So density of water is 1000 kg per meter cube. So our density of fluid is 900 kg per meter cube. Now using this density, we can find out our gauge pressure, that is P is equal to rho GH. So rho is a density, that is 900, which we have found out. G is a gravitational acceleration 9.81, whereas H is the height of that liquid in a column, that is manometer column, that is given in a data 350 mm. Converting it into meter, so I have written 350 into 10 raised to minus 3. So the gauge pressure is 3090.15 pascal. Okay, converting that pressure into a kilopascal, we get 3.09015 kilopascal. Okay, so this is our gauge pressure answer. Now we need to find out absolute pressure. So the formula is atmospheric pressure plus gauge pressure. So I have written 101, that is our atmospheric pressure, plus 3.09015, that is our gauge pressure. The total pressure at our point A is 104.09 kilopascal. Okay guys, so with this we are completing with our chapter 1. I hope that you are clear with the concept and numericals of this chapter. In our next session, we will start with our new chapter, that is properties of gas. Till then, stay tuned and thank you all.